thank you again, everybody, for turning up for the second session this week. I'll skip the correction for the slide from Lecture 2, but I have put the corrected slide up on Google Documents. So if you have a look there, you will see that I've defined the mass flow rate in terms of the volume flow rate, and I corrected the equation for the maximum power to show that the maximum power is the mass flow rate times the jet velocity squared on 2, which is the mass flow rate times the kinetic energy of the jet. The corrections I put are in red, so they will be very easy to see. Okay, so let's move on to Lecture 3, where I'm going to talk some more about turbine efficiency speed control, which is a really important issue, particularly in the context of the ramping time or the starting time or stopping time, however you want to look at it, for hydro turbines, because in the context of high penetration of intermittent renewable energy, hydro turbines are becoming a very good backup resource because they can be turned on quickly and they can be turned off quickly. And in electricity systems that have a free market structure, the hydropower producers often earn many more dollars or rubles per kilowatt hour than the wind farm owners and the solar farm owners, because the hydro turbine owners have a technology that can come on very quickly and can come off very quickly and is generally dispatchable. In other words, it can respond to a requirement or a request from the system operator to ramp up in power whenever that is necessary. So we'll talk a little bit about that. And right at the end of the lecture, I'm going to say just one slide's worth about the hydro resource and the variability in itself of the hydro resource, because it's not entirely dispatchable. You know, hydro power is dependent on floods and droughts and issues like that. Okay, so just to continue our discussion of the various turbine types, of the two types that I talked about in the last lecture, the Francis turbine and the Kaplan turbine. This is what they look like in profile. So Francis turbine is what we call a mixed flow turbine, because the water comes in radially through the blades, exits parallel to the axis of rotation, whereas the water flows through the blades of a Kaplan turbine is more or less in the direction that's parallel to the axis of rotation. When we look in more detail at turbine performance and the matching of a turbine to a particular site, we get away from that diagram that I showed you before, where I had the regions where the cross-flow turbine sits and the regions where the Francis turbine sits. We need to look much more carefully at the performance of individual turbines that would then be selected if you were buying a turbine off the shelf that would be selected for a particular site. And what you see here is a typical turbine performance map. The vertical axis is put in terms of what's called a flow coefficient. I haven't defined what a flow coefficient is. All you really have to know for our purposes is that the flow coefficient is proportional to the water flow rate. So proportional to the volume flow rate in meters cubed per second. So the higher we go on the y-axis, the more water is flowing through the turbine. And I should turn my laser pointer off to make it clearer. And the horizontal axis is proportional to the shaft speed. So this is a typical performance diagram for a turbine. I think this is a Francis turbine, although I'm not sure. So you can find out from the nominal volume flow rate and performance where you sit on this curve. And you can see these lines here are the lines of constant Wicket angle. So these lines here show you how the turbine will perform when the inlet guide vanes, or the Wicket gates as they're sometimes called, are set to that particular angle. And the main point that I want to draw from this is that normally speaking, you want to operate your turbine in its most efficient range. And you can see contours of constant efficiency on this diagram here. And you can see where I've highlighted the contour for 91%. That's the region where ideally you would be operating this turbine. So after you've done a very basic site assessment to determine what your resource is in terms of head and volume flow rate, then you have to start looking in detail at the specific performance of the turbines. And one of the things that we're going to be talking about in this lecture is how we adjust turbine performance for variations in the operating conditions. And I'll go to the next one. I mentioned that the Francis turbine is the most common large hydro turbine. It is made in, there are small Francis turbines as well, but they're not so common. This shows you a cross-section through a Francis turbine where you see the laser pointer now in the spiral casing. That is where the water comes into the turbine. And if you look down on a Francis turbine, you will see that that spiral casing, very much like the nozzle of the cross-flow turbine that I was talking about yesterday, that spiral casing decreases in size as it goes round the circumference of the turbine. And the reason it decreases in size, of course, is that there is water going from the spiral casing through the Wicket gate into the blades on the total periphery of the turbine, because you want as many of the blades as possible to be acted on by the water that is coming through the spiral casing. So the Wicket gates here can be set to different angles, and those angles usually are used when you have the situation of, say, a varying flow rate through the turbine. If, for example, there's a drought and your dam water levels are dropping down, you may have to reduce the power output. When something like that happens, it's usually the case that the head that is available to the turbine does not change substantially, but the volume flow rate changes. And one of the easiest ways and one of the traditional ways to control the turbine under those conditions is through the angle of the Wicket gates. So one of the important features of most types of hydro turbines, and we'll look at the reasons for this again later in this lecture, one of the important features of most hydro turbines is that there's some form of mechanical speed control. Okay, that is a very different situation to what we'll see with wind turbines. And the different reasons or the different ways the turbines are controlled has a lot to do with the age of the technology. Hydro turbines were first used in the days when power electronics was virtually non-existent. And usually a hydro turbine at the beginning of the 20th century had to run at constant speed. And the reason that it had to run at constant speed was that was a way that the generator that is producing AC power for that turbine is producing that power at the same frequency as the grid. So when you're connecting a turbine, whether it's a hydro turbine or a wind turbine, to the grid, you have to be outputting power that is compatible with the voltage and frequency that the grid uses. And in the old days of hydro turbines, the generator ran at a constant speed, which meant that the runner had to rotate at a constant speed, which means that if there's a change in the volume flow rate, that is normally handled by changing the angle of the Wicket gates. And we'll have a look again at some of those ideas later on. Okay, I did a search through Google for images of Wicket gates to give you a better idea of what they look like. This is all I could come up with. This is a small Francis turbine, but is a very convenient one because the Wicket gates are in yellow. The runner is in red and the turbine casing is in blue. So you can see two situations where the Wicket gates are at different angles. These angles here are probably very close to shutdown. The amount of water that would get past the gates in this angle into the runner of the turbine would be a lot less than this case here. You can see the outlet of the turbine. I forgot to mention from the previous slide, that goes into the draft tube. And the draft tube is a diffuser that sits below the turbine that takes the water away from the turbine. And that draft tube may appear to have not a very significant impact on the performance of the turbine. And that's generally true if the turbine is operating at its most efficient point. But when you get into off-design points, when you, say, have a reduced flow rate or something like that, the flow in the draft tube can be very problematic. And a lot of the research that has been done by Ivan's colleagues in Novosibirsk has been about what happens in the draft tube, particularly at off-design conditions. Okay. Just to give you an idea of the size of modern hydro turbines, this graph is pretty old by renewable energy standards. It finishes in 2010, but as far as I know, there haven't been any larger turbines built, that are larger than the Three Gorges turbines in China. And this was a installation at the end of the last century. The turbines, I think, were rated at 875 megawatts. I mentioned, I think in the last lecture, the Ethiopian Renaissance Dam, which is currently the biggest hydro turbine project in the world. The turbines for that dam will be Francis turbines as well, but they are rated at somewhere around 400, I think about 475 megawatts. The other feature to note about Francis turbines is that it looks from the shape of the guide vanes or the Wicket gates that they have to be designed carefully. And you can see that the blades in the runner of a Francis turbine are also quite complicated. And the main reason why Francis turbines are not used for small scale hydropower is simply the complexity of the blading. Compared to, say, something like a cross-flow turbine, this is actually quite a complicated geometry that is much more difficult to build. Okay, so moving on in turbine types, there is a Kaplan turbine. And as I mentioned before, it looks pretty much like the propeller of a ship. Or if you think about issues of cavitation, which is one of the reasons why hydro turbine blades are typically larger or longer than wind turbine blades to spread the load more evenly to reduce the negative pressures on the blades. This actually looks quite similar to horizontal axis turbine. A Kaplan turbine can have pitch control. In other words, these blades can be rotated as I'm showing you with the laser pointer. And sometimes that sort of pitch control can be used as an alternative to Wicket gates. And when we get on to wind turbines, we will see the pitch control of a wind turbine blade is used extensively in the control of wind turbines, mainly towards the upper end of their power curve. Okay, this is a picture that I really like because, again, it shows the scale of these turbines. This Kaplan turbine looks to me to be roughly the same size as the one in the photograph before. You can see a person standing here. It shows you where the water comes in through the Wicket gates and then the water is deflected into the axial direction before it goes through the blades. But it also shows you the generator. And this is a typical arrangement of a large-scale hydro turbine where the generator is directly connected to the blades. And you can see, if you know anything about electric generators, that looks to me like a permanent magnet generator, where each of those rectangles that I'm showing with the laser pointer would be a pole of the generator, and probably a permanent magnet pole of the generator. Permanent magnet generators are extremely important for wind turbines. And when we get on to wind turbines, we'll be learning a little bit about permanent magnet generators and their use with wind turbines. The more poles that the generator has, the lower the angular velocity needed to generate a particular frequency. So this tells me that this Kaplan turbine has a large magnet generator, which probably means that the angular velocity of this turbine is relatively low. Now, as I mentioned before, in the old days, that direct connection of the generator to the turbine would fix the turbine speed so that the generator speed produced AC power at the correct frequency to connect to the electricity grid. Nowadays, we don't have to do that. And one of the things that one of the topics that we'll be looking at later on in this lecture, a bit more next week for hydro turbines and quite a lot when we get on to wind turbines, is how we can connect a generator that is producing asynchronous power compared to the grid to the electricity grid. Okay, just a little bit more on the layout of hydro turbines, and this is a typical one. This is taken from a well-known English language book on turbo machinery, which is a useful introduction to it if you want to look into these things in more detail. What I'm pointing out here is just a couple of points of nomenclature. Naming. So the pipework is usually called the penstock. And the penstock usually starts at the surge tank. And this surge tank here is a typical feature of a hydro turbine system. And the surge tank is there to prevent the formation of standing waves in the penstock. I don't know... If I say the term water hammer, you probably don't understand it. Maybe Ivan knows the Russian equivalent of it. But one of the things that I haven't mentioned to you so far is that when we do the hydrodynamic analysis of hydro turbines, we assume that the water is incompressible, that its density doesn't change. But that's not entirely true. The density of water can change minutely if there is a significant pressure change to the water. And if you have a turbine, say, like this Pelton turbine that has a valve in it before the nozzle, and you suddenly turn off that valve to stop the turbine operating, that can generate standing waves in the penstock. And that does that. I can't tell you exactly offhand how this happens because I've forgotten the theory for it, but that causes waves in the pipework that if you don't have something like a surge tank, those waves can damage the pipe equipment. So the idea of a surge tank is just a tank that is open to the atmosphere that allows the water level to go up and down slightly just to absorb those waves that are generated in the penstock if you shut the valve off. As I said, the English word is water hammer. I'm not sure. There's probably a Russian equivalent and I would not know what it is. Okay, back to questions of efficiency. And I've put up a typical torque, power, and efficiency curve for a Pelton turbine. And so the vertical axis is all those three quantities. Power here, these two lines here. Torque is the more or less straight line going down there. Sorry, no, that was the efficiency. The power is not shown, just the torque and the efficiency. And the x-axis is proportional to the velocity entering, the circumferential velocity of the Pelton wheel divided by the jet velocity. Our simple theory that I derived last lecture, says that the maximum efficiency of 100% occurs when the Pelton wheel circumferential velocity is half the jet velocity. Okay, that's an analysis that assumes ideal behavior of the water flow. So that gives 100% efficiency. And I mentioned it yesterday, and I'll mention it again. I find it extremely surprising that something as crude as a Pelton turbine can actually achieve an efficiency close to 95%. So what you see, the difference between those two efficiency curves is really all about the frictional losses that we have ignored in the analysis that we did yesterday. So including those frictional losses, the maximum efficiency goes down to something close to 95% for a well-designed Pelton turbine. And importantly also, it occurs at a lower value of the speed of the wheel compared to the jet than the theoretical maximum. And I also mentioned it yesterday, but it's important to mention again, the main reason for the difference between the ideal and the actual curve is the air drag of the Pelton wheel, the frictional resistance of the Pelton wheel rotating in air. Okay, the losses that occur in a Pelton turbine, most of that difference between the ideal and the actual turbine is actually air resistance of the turbine. So if you could operate a Pelton turbine in a vacuum, then you would push the actual efficiency curve much closer to the ideal curve. And again, I think that's extremely surprising because it means that very simple aiming a jet of fluid at the buckets and letting that rebound from the buckets, that can produce a surprisingly accurate turbine. And a Pelton turbine has a particular niche in the turbine market because it is the best sort of turbine to have for high heads and relatively low flow rates. Okay, now we come on to looking a little bit more at how we control the operation of a turbine. And again, the Pelton turbine is a relatively simple example to discuss this. And the basis of what I'm going to say is the observation that I've made on the right-hand side here. If you have a turbine installation, it's more likely that the flow rate is going to change rather than the head is going to change. Okay. If you have a Pelton turbine, you're not going to make a substantial difference to the difference in elevation of the water level in the dam to the Pelton turbine. You'll make a small difference. If there's a drought happening, that elevation is going to be lower, but that change in elevation due to water levels is probably going to be small relative to the remainder of the elevation difference. The other thing you have to think about is that looking at the equations for the frictional losses that we studied yesterday, the frictional losses depend on the flow rate. So if you change the flow rate, you're going to change the frictional losses, and that will change the effective head that's available to the turbine. However, again, the change is not going to be large. So the usual situation that you have with hydro turbines, if, say, you have to preserve the water level in the dam because it's a drought, or alternatively, you have to reduce the flow rate to accommodate a reduction in the power output, maybe as you've been told by the system operator to reduce the power output, what you have to do is change the flow rate more or less a constant head. And again, we're talking about how we can do this mechanically, because this is part of the history of hydro turbines. Pelton turbines have been around for 150 years or so, and these mechanical methods of controlling the operation of a Pelton turbine were developed before engineers and scientists had any means of doing electrical control. Okay, and the usual way that it is done is shown in the top two diagrams here, with what is called a needle valve. And what I'm showing with the laser pointer is the needle valve here. And that needle valve has a cross section that changes with position, and you simply move that needle valve into and out of the nozzle. So that, for example, if a turbine is operating at full load, the needle valve will be somewhere like that. If you have to reduce the load, the needle valve will close into the nozzle, cut off the flow to some extent, and reduce the volume flow rate. And that's a very simple way of controlling the operation of a Pelton turbine. And it usually works quite well, because the timescales over which you typically have to change the operation of a Pelton turbine are large times compared to the times over which, say, wind power or solar PV power changes due to changes in wind speed and changes in radiation level. So if you think about it for a moment, you've got the situation where the head is staying the same, but the volume flow rate can change. What that means in terms of the operation of the needle valve is that valve has to be adjusted in area so that the velocity coming out of the jet does not change. Okay, because if you go back to the lecture that I was talking about, the slide from yesterday that I corrected today, that says that the jet velocity coming out of here, the ideal jet velocity, is the velocity that converts all the head into kinetic energy. And if the head is not changing significantly as the flow rate changes, that means that velocity doesn't change. And that also means that the angular velocity of the Pelton wheel doesn't change, which is exactly what you want if you're wanting to produce electricity that has the correct grid frequency as your load changes. So if you think of the relationship between velocity, area, and flow rate, basically what you have to do to maintain the same velocity is to reduce the outlet area of the nozzle as the flow rate reduces. And that's exactly what the needle valve does. Here is, down the bottom here, is a better description of how the needle valve works, because it shows the mechanism by which it is moved into and moved out of the nozzle. So the mechanical control is extremely simple. And this control of the needle valve for a Pelton turbine is probably the most complex control that you have on a hydro turbine, because changing the angle of the Wicket gates is actually easier to do than changing the position of the needle valve. So that's the primary way in which load adjustment is done for hydro turbines. Okay, I put this slide in to just let you know that there are hydro turbines that do not operate on a significant elevation difference and get their energy from potential energy. There are what are called hydrokinetic turbines that use the kinetic energy of the water flow. These can be horizontal axis turbines, as you can see on the left here, and as you can see in this photograph here, which is taken from a study that Ivan and I were involved in that was done at the Danish Technological University. This is a big water flume, a wind tunnel that has water in it rather than air. This water flume is 3 meters wide by 1 meter high. And so it's one of the largest flumes that I know of. And this is an experiment where you can see 2 hydro turbines, one behind the other. And this experiment was looking at how the performance of particularly the second turbine is affected by the presence of the first. Because the first turbine is taking as much kinetic energy as it wants from the water, which reduces the kinetic energy that's available to the second turbine. And how you maximize the total power output of those turbines in a situation like that is a very important research area, both in hydro turbines and also for wind farm layout, how you put wind turbines in a wind farm when they're going to be close enough together that you get those sort of interference effects. And they're made worse because often if you're going to put hydro turbines in a river, for example, then you want to confine or minimize the part of the river that has turbines in it. So this sort of situation where turbines are in close proximity is an important practical problem that people are studying. So that's another horizontal axis turbine. Here is a vertical axis turbine. So the water would be coming into the page in the direction of the laser pointer, and these blades rotate around a vertical shaft. There is another version of that turbine. This is normally called a transverse axis turbine, where the axis of rotation is still transverse or normal to the water flow, but that axis is horizontal. And this is said to be a really good technology, particularly if you have restrictions in height, maybe due to the height of water in a river. So that's just to put in there to emphasize that the hydro turbines that produce power from the available head are really only one type of hydro turbines, the hydrokinetic turbines, which look much more like wind turbines that we're going to be studying probably next week. They have a role to play in the scheme of things as well. Okay, just a little bit now about generators and how the output power from a generator is fed into the grid. All I'm showing here is 2 things. One is to give you a definition of what are called synchronous generators. When the term synchronous generator is used, it does not mean that it's synchronous with the electricity grid. What it means is that the frequency of the electrical power is synchronous with the angular velocity of the turbine or the generator shaft. And if you have a permanent magnet generator and you have a number of poles on that generator, the frequency is defined by the number of poles. So if you want to have something like 50 hertz power out of a slowly rotating turbine, then you have to have a generator with a large number of poles, which means a physically large generator. And for also the other type of generators are asynchronous, usually an induction generator, which are often used for small turbines. They operate with slip between the angular velocity of the shaft and the frequency of the power coming out. That's why they're called asynchronous generators. I'll be talking quite a bit more about the structure of the generators and how they work when we get on to talking about wind turbines. One of the important things for what I'm going to be saying next is that usually speaking, the generator inertia is greater than the turbine inertia. When we get on to wind turbines, we have the reverse situation because wind turbine blades are large the blade inertia is usually significantly greater than the turbine, than the generator inertia. Okay, now just a few fairly simple words about how we connect an electricity generator to the grid, because even if we're primarily interested in the hydrodynamics of hydro turbines or the aerodynamics of wind turbines, we still need to know at least something about what happens after the power has been absorbed from the fluid. So typically we have a generator. PMG stands for permanent magnet generator. And that generator is receiving a torque at a particular angular velocity. And the old method of doing the grid connection is that frequency or that angular velocity would be set so that the power coming out of the generator was the same frequency as the grid. What's happened since hydro turbines were first developed, and it's happened at the same time as the explosion of the wind energy industry and the explosion of the photovoltaics industry, is that the power electronics that are available are able to handle situations where omega and Q can vary randomly with time. And the way that is done is usually to, first of all, rectify the alternating current that comes out of a permanent magnet generator. Typically, a permanent magnet generator produces three-phase power. And if it's connected to a wind turbine, then that frequency of that power is changing all the time. So the power electronics that are associated with that, first of all, convert it to a DC, put it through what's called the DC bus, which filters out some of the ripples in the DC power, and then puts it into an inverter whose job it is to produce the output power that has the correct frequency and voltage for the grid connection. Now, again, I'm going to be talking more about this setup when we deal with wind turbines, but the reason that I put it in this lecture on hydro turbines is to point out that the difference between the system that we see here and the system that we see here is of the order of 100 years. So this is what hydro turbine installers had to do when hydro turbines first became popular at the beginning of the 20th century. This is what you can do now if you have to. So even if you have a hydro turbine, you don't necessarily have to design it so that the generator is producing all the time the exact frequency of the grid. So I'll move on to that question again when we come on to the section on wind turbines. What I want to do now is talk to you a little bit about the response times of hydro turbines, because this is an extremely important aspect of hydro turbine use in the context of electricity systems that has a large amount of renewable energy. And I talked a little bit of the reason for that in the first week's lectures, that if you have a lot of wind power and or a lot of solar power on your grid, you're going to get very significant fluctuations in both the total power that's available to the grid and also the individual wind farm and solar farm power. And if you're designing a grid or operating an electricity grid like that, then you need other generators that are able to respond to those fluctuations. And we saw from examples that I showed you how rapidly wind power can fluctuate with time. And hydro turbines is one of the technologies that's very suitable for that purpose. Gas turbines is another technology that is very suitable to be ramped up and ramped down with wind and solar power. Also, most forms of storage are able to ramp up and ramp down quickly as well. The value of being able to respond quickly for the owner of the hydro turbine facility is that they usually get paid a top price for the electricity that they provide. Often what happens when you have a significant amount of renewable energy connected to the grid, the wind farm owners and the hydro and the solar farm owners will get a fixed price for the electricity through a power purchase agreement. But the owners of the hydro turbines and the owners of the gas turbines, because they are able to make up both the deficit and the excess of the renewable power, they typically get paid a lot more for their electricity. Okay, so the expansion of renewable energy into electricity grids has actually opened up a number of opportunities for the more conventional electricity generating technologies. And that's the main reason why the turbine response time is important. If we have a technology that cannot respond quickly, then it's not going to fit well with a electricity grid with a lot of renewable energies. That's one of the reasons why nuclear power is not a good option for an electricity grid with a large amount of renewable energy, because nuclear power cannot respond rapidly to changes in load. Okay, there's a lot of very useful practical information on the application of these issues associated with turbine response time. This guide, this is the International Institution of Electrical and Electronic Engineers. It's a US organization that generates a lot of standards for electricity production and connection to the grid. And what they talk about in terms of response times is it's a twofold issue. First of all, there's what they call a water inertia time. If you have a hydro system whose turbine is turned off, then usually what that means is that there's a valve immediately behind the nozzle of a Pelton turbine, or before the entry to a Francis turbine, and that is simply shut off. All the penstock and the pipework will be full of water, but if the turbine needs to be turned on and that valve is open, it's going to take a certain time for that water to reach full speed. And that is what the water inertia time is. There's a formula for it. This is the accepted international standard. What they call the starting time depends on the rated flow rate. It depends on G and the head. It depends on the length of the pipework and the cross-sectional area of the pipework. And this, again, is a situation where it's possible to do a very simple analysis and get an answer that is surprisingly useful. Imagine we have a supply of water with a head H, and that supply of water is contained within a tank whose cross-sectional area is large compared to the cross-sectional area of the pipework. So this might be a lake behind a dam and reservoir. This would be, to make life simple, a length of constant area horizontal pipe. Now, if you do a momentum balance on the water in that pipe, then its mass times acceleration is going to be equal to the net force acting on it, which will be the hydrostatic head at the entrance to that pipe. So that's obviously a very simple-minded statement that involves a considerable number of approximations. If you know anything about the unsteady form of the Bernoulli equation, you can actually apply that to this situation and clarify what assumptions you're making and how important they are likely to be. But if you start with this equation here, then the next line is effectively the equation that you saw in the last slide from the IEEE standard. So basically, the idea is that at time t equals 0, there's no water coming out of this pipe. At time equals 0, any restriction at the outlet is removed. This equation holds, and therefore the time that's required to get up to full speed is going to be that given by that formula there. So that's one part of the time response equation. The other part of the time response is the what's called the mechanical inertia. In other words, if you have something massive like a Pelton wheel, then it's going to take the Pelton wheel a certain amount of time to reach full speed. And we saw from what I said about the needle valve and how that controls the water in the jet or the volume flow rate in the jet, the speed of the Pelton turbine that you need is more or less independent of the power output. So no matter how much power the system operator has asked you to provide in the next 10 seconds, you've got a fixed speed that you have to get your Pelton wheel up to. And that involves the considerations that you see here, which are not so easy to explain. I don't have a nice, simple explanation for why equation 3 and equation 4 work, but this standard is a distillation of many years' experience on operating hydro turbines, and we can be assured that it works. What I've highlighted here is just a statement that typically, the generator is the main contributor to the inertia of the system. So the mechanical inertia and the water inertia are fundamentally different. Okay, they have different causes. They do interact because obviously the velocity coming out of the nozzle of a Pelton turbine, its variation with time depends on the water inertia, and the acceleration of the Pelton turbine is also going to depend on that velocity. So they do interact, even though their causes are fundamentally different. And so what you get is a situation like this. Imagine that a hydro turbine, and this figure comes from that IEEE standard, and I forgot to mention earlier that standard's available freely online. So if you're particularly interested in this topic, which I think is a fascinating aspect of hydro turbine operation, you can download that standard and look in more detail. So here's a typical example that they give. The turbine has to, as quickly as possible, increase in power output from 50 to 55 megawatts. And the usual form of the response time when the fluctuation in the output power is within certain limits of the new set point, that defines the the response time. And that, as far as I understand, that value of the order of 15 seconds is pretty typical for a turbine, a hydro turbine setup. And normally that is considered fast. If you have a hydro turbine that can respond to required changes in the load in that sort of time, then that makes it a very appropriate backup technology for the intermittent renewable energy generators. One thing you might like to think about: what if you had to do the reverse? That you've changed the set point of the turbine to go to 55 megawatts, and then sometime after 35 seconds, the system operator asks you to reduce power to 50 megawatts. Is the time required to do that likely to be greater or less than the time required to ramp up? Interesting question. I think the answer is less, because the action of the needle valve, or the needle valve, can reduce the flow rate more rapidly than the water inertia time allows you to increase it. Interesting. Okay, so this is, I didn't check the time. How are we going for time? I forgot to put my watch next to me. I'll just wait for a moment. Okay, I just got my clock and I see that we're very close to finishing anyway. What I've done here is just put up a single slide to point out that hydropower is often considered as a dispatchable energy technology. In other words, it can respond rapidly to requests to change its power output, but it's not totally free of intermittency issues. For example, this is just a typical what's called a hydrograph. It shows the flow in a river as a function of time over a year. Okay, so if that river is feeding a dam, then clearly the amount of water that flows into the dam can change rapidly over time. I'm not sure exactly where this is taken from, but this looks to be like a climate that has a reasonably uniform rainfall throughout the year. If you have a climate like a Mediterranean climate, for example, or indeed a climate like you get in Siberia and Canada, where you don't get any water coming into the dam during winter, then the seasonality can be extremely important. Also, too, what is usually done in defining the capacity of a particular hydro resource is to do what's called, or to determine what's called a flow duration curve. And what a flow duration curve is a plot of the volume flow rate, say, in a river, versus the percentage of time that flow rate is exceeded. So it's sort of like a cumulative probability distribution for a river flow rate. And usually if you have a turbine, say a hydrokinetic turbine, which is sometimes called a run-of-the-river turbine, or a turbine that is taking water from a river, what you usually do is set your design flow rate to be something like the flow rate that's exceeded, is available for 80% of the time. Sorry, I had that round the wrong way. Where it says percent exceedance, it actually means the opposite of that. 80% here means that you will get that flow rate 80% of the time. Okay, I just pointed that out because the resource availability is an extremely important issue for wind and solar power, which are significantly more intermittent than hydropower. But I just wanted to point out that hydropower is not entirely free of those intermittency effects. So with that, I'm pretty sure that's the end of the presentation. Yes, it is. So I'll stop sharing the screen there. If anybody has any questions, you can put them in the chat or unmute and ask them. Next Tuesday, I'm pretty sure I will finish off the lectures on hydro turbines, and Wednesday we'll start on wind turbines. So does anybody have any questions they want to ask before we finish today?
I have a question.
Mm-hmm.
One question about dark side of Pelton turbine. So what do you expect the lifetime of this turbine, and what is the weakest thing on this line? I mean, the Pelton needle wave Pelton turbine, exactly, because I think splitter could be changes with time. Yes.
Yes. I don't know a lot about Pelton turbines because I've actually never worked on them. I've been a little bit involved in some computational fluid dynamics studies of them. And with those computational fluid dynamic studies, they're the things that are needed to get the fine details of the design of the buckets, for example. You really, like deciding on the number of blades and the geometry of the blades of a cross-flow turbine, you need to do detailed CFD to design the buckets. I am getting to answer your question, by the way. What is related to that is that with CFD, you can do some pretty simple estimates of the effects of cavitation. Okay, cavitation, to a first approximation, all you need to do is in your computational fluid dynamics simulation, find the points in the flow field where the pressure is less than the vapor pressure. Okay, that's because CFD gives you the pressure at every point in the flow that you are simulating. That in principle is an easy thing to do. And so what people use CFD for is to investigate the cavitation in Pelton turbines. And as far as I understand, cavitation is one of the main limitations on Pelton turbine operation. And I think can be responsible for, say the erosion of the splitter plate and also the buckets, because, you've got the water hitting those buckets at 100 meters per second. It's a pretty substantial impact. I don't know what that means in terms of typical Pelton turbine lifetimes, but I'll see if I can get some information on that and share it with you. It's a good question. The other issue that comes up that I haven't mentioned before is what happens if you have any dirt or impurities in the water flow. If you have solid particles in the water, they're impinging on the buckets at 100 meters per second, and that's not good either. So yeah, I'll see if I can find any information of that. Okay, and any other questions that people might have? Okay, so we shall finish for today, and I will see you again on Tuesday. And thank you for your attention.